Hello everyone, in this video I am going to explain about pulse modulation techniques. If you like this video, please subscribe to my channel and share to your friends. In this pulse modulation techniques, we have two types are there. The first one is that pulse analog modulation technique and second one is that pulse digital modulation technique. In this pulse analog modulation technique, we have three types are there. Those are pulse amplitude modulation, pulse width modulation, and last one is that pulse position modulation. And in pulse digital modulation techniques, we have three types are there. Those are pulse code modulation, delta modulation, and last one is that differential pulse code modulation. Now we will see about that pulse analog modulation techniques. In that, the first one is that pulse amplitude modulation. So in this modulation scheme, the amplitude of a high frequency carrier is varied in accordance with the sampled values of a message signal. So here this M of t is nothing but a message signal and C of t is nothing but a high frequency carrier. So the amplitude of this carrier signal is varied according with the message signal. So here these are the pulses. The pulse amplitudes are varied in accordance with the message signal. So this is the output of a pulse amplitude modulation. There is nothing but here S of t. This is about pulse amplitude modulation. And next one is that pulse width modulation. So in this modulation scheme, width of a carrier pulses are varied in accordance with the sampled values of message signal. So here this M of t is nothing but a message signal and C of t is nothing but a high frequency carrier and S of t is the output of a pulse width modulation. If you see here, these are the pulses. According to the message signal, the pulse widths will be varied. So this is about that pulse width modulation. Generally, this pulse width modulation is used for controlling the speed of a DC motor. And next one is that pulse position modulation. So in this modulation scheme, the position of a high frequency carrier pulses is changed in accordance with the sampled values of a message signal. That is here, this is the message signal and this is the carrier signal. The carrier signal pulses changed their position accordance with the message signal. So this is about that pulse position modulation. Generally, PWM is generated using 555 timer in monostable multivibrator mode and PPM is generated using 555 timer by using PWM as a trigger signal in the monostable multivibrator mode. So this is about pulse position modulation. And next one is that comparison of these three modulation techniques. So when you're going for the bandwidth, the PAM has less bandwidth compared with the two other techniques, that is PWM and PPM. And if you see that the signal to noise ratio is less for PAM and it is moderate for PWM, the signal to noise ratio is high for pulse position modulation. And if you see the complexity, PAM has less complexity and PWM has moderate and the complexity is more for PPM. But this PPM is the most effective pulse analog modulation scheme in terms of signal to noise ratio. So this is about the comparison of PAM, PWM and PPM. And next we will go for pulse digital modulation techniques. In that, the first one is that pulse code modulation. So in this pulse code modulation scheme, we first sample the analog signal and then we will quantize it and then it will be converted into levels and after that they are encoded. Then send it in the form of a digital codes. If there is a n-bit quantizer and the sampling rate is fs, then the bit rate is given as n into fs, where n is the number of bits, fs is the sampling rate. So the bit rate is given as n into fs bits per second. Here the sampling must be done at a rate greater than or equal to the Nyquist rate in order to avoid the aliasing effect. And at the same time, higher will be sampling rate, easy will be reconstruction of a signal at the receiver. So in this pulse code modulation, the bandwidth requirement is minimum when RB by 2 and maximum when it is RB. If uniform quantizer with a step size delta, if it is used, then the delta is given as Vmax minus Vmin by L, then the delta is given as Vmax minus V minimum by L, that equal to Vmax minus V minimum by 2 to the power of n, where L is the number of levels. So the maximum quantization error will be given as delta by 2, and the quantization noise power for uniform quantization is given as del square by 12. Signal to quantization noise ratio for pulse code modulation for sinusoidal input is given as signal to noise ratio is equal to 6n plus 1.76 dB, where n is number of bits of quantizer. So as the number of bits of quantizer increases, signal to noise ratio also increases, but at the same time the bandwidth requirement for transmission also increases. So this is about the pulse code modulation. And next we should know about the companding. So here the companding is nothing but compression of a signal at transmitter end and the expansion of a signal at the receiver end. So this companding is of two types. One is mu-law companding and second one is A-law companding. For mu-law companding and A-law companding, the equations are given as V out equal to this one, and here also for A-law companding, V out is given by this equation. Here mu max equal to 255, where A max equal to 87.6. In this companding we have to remember the 2 points. One is companding is done to avoid nonlinear distortion of a channel, and second one is that companding is very widely used in telephone systems to reduce nonlinear distortion and also to compensate for signal level differences between soft and loud talkers. So this is about the companding. And next one is that differential pulse code modulation. When the samples of a signal are highly correlated, then we go for differential pulse code modulation in order to save the bandwidth or using the same bandwidth at a higher data rates. So this differential pulse code modulation will be used the principle of prediction. So this is about that differential pulse code modulation. And next one is that delta modulation is the special case of differential pulse code modulation. It is called 1-bit differential pulse code modulation as it transmits only 1 bit per sample. In delta modulation, problem of slope overload occurs if input is changing very fastly. So here the slope overload occurs when delta by Ts is less than of d of m of t by dt. To overcome this slope overload error, we choose that optimum size of delta such that by considering this equation. And last one is that the message signal m of t is given as am into cos 2 pi fmt, so that the optimized value of this delta by Ts equal to 2 pi fm into am. And in this delta modulation scheme, the second type of error is granular noise. That is nothing but hunting noise, which occurs when message is almost constant. And for this delta modulation scheme, the signal to noise ratio maximum is given as 3 by 8 pi square into fs by fm whole to the power of 3, where fs is the sampling frequency and fm is the message bandwidth. So this is about the delta modulation. And next one is that adaptive delta modulation. In this one, the step size is chosen in accordance with the message signal sampled value to overcome slope overload error and hunting error. If the message is varying at a high rate, then the step size is high, and if the message is varying slowly, then the step size is small. In case of ADM and DM, the bandwidth requirement is almost same. So thank you very much for watching this video. To watch more videos, please subscribe to my channel OPENBOX Education.